Okay, here we have a couple problems on motional EMF. The first one is number 23 from chapter 20. And we are told that there's a truck carrying a long beam. The beam is 15 meters. And it's traveling at velocity v. And then there's a collision. And then the bar goes flying. Right? This thing goes flying by itself. It turns across the highway. It's 15 meters still, and its center of mass is traveling north while the beam lays horizontally along the east and west directions. Okay, we want to know what is the EMF in the metal beam. And how we're figuring this out is we're using the Earth's magnetic field, which is 35 microtesla at that point. The velocity is 25 meters per second. And then, so we plug in our formula, 35 microtesla times the length, which is 15 meters, times the velocity, which is 25 meters per second. And we get a value of about 0.0131, and that gives us 13.1 millivolts. So that was a pretty straightforward problem, kind of fun. Next, we'll move on to number 26. Where we're told that the space shuttle deployed a wire that was dragged along the magnetic field lines of the Earth. So we had a space shuttle, and then it's dragging a wire across the magnetic field lines. And then we're given a length, it's 20 kilometers. We're given a velocity. We're told it's 7.86 times 10 to the 3 meters per second. And then we are told that at that point, the perpendicular magnetic field is 1.5 times 10 to the negative 5 Tesla. So again, we just, and we were asked to find the EMF because this is going to be used as a power source, right? What's the induced voltage here? And we just need to plug in our formula again. So we just put in the values we're given. 7.86, 10 to the 3, and 20 times 10 to the 3 meters. This gives us a value of 2358 volts. It's quite a lot, actually. Next is problem 30. A very similar problem. We're given a circuit with a magnetic field pointing into the page. Then we are given a bar that is traveling along the length of the circuit. Side length L, we're given a resistor over here. And we know that there's going to be an applied force pushing the bar along due to the magnetic field, which is in here, B. Right? So we're told that the resistor is 6 ohms. We're told the length of the side is 1.2 meters. We're told that the magnetic field is 2.5 Tesla. And we are asked to find what is the speed that is going to produce a current of 1 amp in the resistor. Okay, so to find the speed, we can use these identities that we know. We have E is equal to BLV, right? We also know it's equal to IR. and we want V. So then what we do is we take IR to the other side, or sorry, BL to the other side, IR over BL. And we have values. We know the magnetic field strength, we know resistance, we know the length, and the current. So we plug all these in, right? 1 amp times 6 ohms over 2.5 Tesla times 1.2 meters. And this gives us a value of 2 meters per second. Okay, next we are asked to find the power delivered to the resistor. We know that power is equal to I squared R. We know the current is 1 amp. We know the resistance is 6 ohms, so that's going to give you a value of 6 watts. We're asked to find the magnetic force magnitude exerted on the bar, and we know that magnetic force from before is equal to the field times the current times the length. That's going to give us 2.5 Tesla times 1 amp times 1.2 meters. That's going to give us a value of 3 newtons. So I took this identity from, I believe it was chapter 19. I think we just went over some of those problems. Then we're asked to find the instantaneous power from the force on the bar, right? Instantaneous power is force times the distance. Sorry, that's wrong. It's force times the velocity. This is an identity from basic mechanics. So we have 3 newtons times the velocity, which was 2 meters per second. And that gives us a value of 6 watts. So a few straightforward problems on motional EMF. Thanks.